So hello, my name is Kevin Boyd. I work under Dr. Raphael Kleiman on photovoltaics research. So my research is concerned with the use of silver nanoparticles to trap light inside solar cells. So when you put some nanoparticles on top of a solar cell and shine light on it, the nanoparticles will grab the light and scatter it into the cell. The scattered light travels at a higher angle, travels along a longer path through the cell than a light that's not scattered. Therefore you get increased absorption. Now, one of the issues with using silver nanoparticles is that they absorb some of the light themselves. This light is lost as heat and doesn't generate electricity. So what we want to be able to do is quantify the absorption losses in nanoparticles. So what I have here is a nanoparticle film that I've created, and as you can see, the shapes and sizes of the particles are not, there's no definite shape of the particles. They're random and blob-like in shape. So what I want to do is quantify how much absorption we expect to see in these nanoparticles. This absorption is parasitic and we want to minimize it as much as possible. So what I worked on are some scattering models for light with nanoparticles. So according to me scattering theory, when light is incident on nanoparticles, a fraction of the light is scattered, which is what we want, and a fraction is also absorbed. The absorption in the nanoparticles is quantified with this absorption cross-section. The bigger the absorption cross-section is, the more light is taken away by the nanoparticles. We want nanoparticles with a very low absorption cross-section and a very high scattering cross-section. So given a nanoparticle film, we would like to quantify how much light is being absorbed in it. So according to the scattering theory, the absorption cross-section is given by the product of the wave number and the imaginary part of the polarizability of the particle. Now the polarizability of a particle is given by this expression here. The polarizability is essentially a measure of how easy it is to polarize the electrons in a nanoparticle. So this expression that I've shown here is for nanoparticles of an ellipsoidal shape. So as you can see from the nanoparticles in this picture, they don't conform to spherical shapes, which is typically the problem treated with my scattering, or me scattering theory. So using the polarizability for an ellipsoidal particle, we can attempt to predict what the absorption cross-section is of this nanoparticle film. So how do we do this? Well, the inputs to this model, there are a few of them. So first off, we need to know the dimensions of the particles we're dealing with. As we can see that each particle in this film has a different shape and size. We also need to know the type of surface on which the nanoparticles are deposited. In my studies, I have used quartz. So we need to know the material properties of quartz. The material property in question is the dielectric constant of quartz, which is about 1.5. So taking that into account, so we have the inputs that we need are the particle dimensions and the dielectric constant of quartz. So we have the dielectric constant of quartz. Now the question is, do we have the, now we need to extract the particle dimensions. So what we do is we take a scanning electron microscope image of our nanoparticle film, and we use an image analysis software to draw ellipses around each particle. From each of these ellipses, we can extract the major and minor axis of the ellipse. Those are our particle dimensions. But that's only the particle dimension in the plane of the surface. We also need to know particle heights. Since we don't know particle heights, I have used an effective height constant, which essentially says that all particles are at this effective height right here. And then running the model through, we can predict what the absorption cross-section will be. So you can see here the solid on this curve here, the solid line is the absorption cross-section, and then these circles here are the absorption cross-section that I have measured experimentally. And you can see that there is good agreement between the model and the experiment. So what's the purpose of this modeling? If we can measure this in an experiment, why do we need to do the modeling? Well, this model is performed on a transparent substrate. So on a transparent substrate, we can directly directly measure the absorption cross-section. On a non-absorbing substrate, such as one that you would use, On an absorbing substrate, such as one that you would use for photovoltaic applications, the substrate will absorb some light. And so you can't directly measure the absorption cross-section of a nanoparticle film because you can't decouple the absorption that happens in the nanoparticles with the absorption that happens inside the substrate. So the purpose of this modeling is to be able to quantitatively model the absorption cross-section on a non-transparent substrate. This will allow us to do quantitative calculations and not rely on being able to experimentally determine the absorption cross-section on an absorbing substrate.
Well, you got your P and you take your N and you make a p-n junction. It's got an electric field that's built right in that gives it special function. Cause when you shine the light and the wavelength's right, you can gather some charges, and they'll do the work of maybe charge a battery or power of electric barges. Solar energy, solar energy. We can have our fun with the power from the sun using good old PV.